The notion of causality plays a central role in science. This is an introductory presentation on how causal relationships are treated in scientific research. This presentation has two parts. The first part describes how causal relationships are conceptualized in science. The second part describes how causal relationships are represented in scientific experiments. What is causality? What do we mean by causal relationship? In a way, this is an easy question, because everyone already knows what it is. Causality is one of the most fundamental ideas that we humans share. One of the first things that parents teach their children is not to play with fire. Because when you play with fire, you can get hurt. We don't teach children simply not to play with fire. We teach them the reason why they shouldn't play with fire. And the reason is that there's a causal relationship between playing with fire and getting hurt. Of course, we don't use adult words like causality when we're speaking with toddlers, but that doesn't change the fact that the idea of causality is implicit even in our lessons with very young children. One way to think of causal relationships is as if-then rules that link two events. Now let's add graphics to make the if-then rule more explicit in our illustration. We have formal names for the two events. The first event, the event that does the causing, is called the cause. In our example, the cause is playing with fire. The second event, the event that gets caused or is influenced by the cause, is called the effect. In our example, the effect is getting hurt. People often refer to causal relationships as cause and effect relationships. With these terms, cause and effect, we can now update our answer to the question, what is causality? It's an if-then rule that links cause and effect. Before we finish this introductory section on causality, let's talk briefly about why. Why do we care about causal relationships? Why does it play such an important role in science? First, in our everyday world, causality is one of the principal ways that we make sense of our world. Just think of it. What would our conception of the world be like if we didn't have if-then rules to explain how events in our world are related to one another? It's inconceivable because the concept of causality is so deeply embedded in the way we look at the world. In the same way, the concept of causality plays a central role in much of science, particularly in quantitative research. In scientific theories, causal relationship is the way that we explain natural processes. Well-developed scientific theories are causal models. Second, knowledge of causal relationships can give us tremendous power over our dealings with nature, because it allows us to predict future events. Just look around. All the modern electronic devices like the computer or mobile device that you're viewing this presentation with was made possible by a whole host of scientific theories. And at the heart of each of those scientific theories are if-then rules that we call causal relationships. They allow us to predict the consequences of our actions. One of the main functions of scientific experiments is to test causal relationships. Let's now see how causal relationships are represented or modeled so that they can be tested with scientific experiments. How do you test causal relationships? In science, when we suspect that a causal relationship exists, we can test it using scientific experiments. But we can test causal relationships with scientific experiments only if we devise ways to measure the cause and the effect. More formally, we would say that to test a causal relationship with scientific experiments, we need to operationalize the cause and the effect with variables that can be measured. Now, this may sound somewhat complex if you're not already familiar with these words, but the ideas behind them are straightforward. Let me show you with our example. Here's our causal relationship. If you play with fire, then you get hurt. To test this causal relationship with a scientific experiment, we need to operationalize the concepts playing with fire and getting hurt. That is, we need to represent the cause and the effect in ways that they can be measured. So let's do that. Here's the cause playing with fire. Let's represent it with a variable called play with fire. We now have a variable called play with fire. In scientific research, the variable that represents the cause in a causal relationship is called the independent variable. Our independent variable, play with fire, can have one of two values, either yes or no. To operationalize the concept playing with fire, we need to specify clear rules for how to determine the value of the variable play with fire. That is, how to determine when a person is playing with fire and when a person is not playing with fire. More generally, in scientific research, the issue of how to represent and measure different concepts that we are interested in is a major topic in itself. But this issue is beyond the scope of this presentation. So in this presentation, we will assume that whenever we introduce a variable, there's a clear set of rules for measuring it, that is, for determining its value. Now let's operationalize the concept of getting hurt. Now we have a variable called burn hand that represents the concept of getting hurt. The variable that represents the effect in causal relationships is called a dependent variable. Our dependent variable burn hand, like our independent variable play with fire, can have one of two values, either yes or no. You may have noticed that we made a subtle conceptual change. Burning hand is a more specific concept than the general notion of getting hurt. That is, burning one's hand is just one of the many ways that a person can get hurt. This is typical in scientific research. We often begin with abstract or general concepts in the causal relationships we want to test, but when we try to operationalize the concepts, when we try to come up with specific rules for representing and measuring the concepts, we often find ourselves using more concrete concepts. One reason is that concrete concepts are usually easier to measure. Also, operationalizing a concept often forces us to think about the specific aspect of the concept that is truly relevant to the causal relationship we're interested in. In our example, while we spoke of getting hurt, we were implying a particular way of getting hurt. We were implying that you can get burned if you play with fire. Sometimes novices to the scientific method confuse the terms independent variable and dependent variable. Remember this, the dependent variable depends on or is influenced by the independent variable. The independent variable does not depend on and is not influenced by the dependent variable. Now is a good time to pause this video and look at this picture carefully. What does the arrow say about which variable is dependent on and which variable is independent of the other? Once you're clear about this picture, you will never be confused by independent variable and dependent variable. Given our new terms independent variable and dependent variable, we can now update our answer to the question, how is causality modeled in scientific experiments? We model them by operationalizing the concepts of cause and effect as independent and dependent variables. In scientific literature, the term independent variable is often abbreviated as IV, and the term dependent variable is often abbreviated as DV. We need one more piece of information to complete our causal relationship model. So far, we've specified that the independent variable play with fire influences the dependent variable burn hand. But how does this independent variable influence the dependent variable? In our causal model, there are a number of different ways we might specify how the independent variable affects the dependent variable. One option is that when play with fire is yes, then burn hand will always be yes. In general, scientific causal models, especially those dealing with human behavior, do not specify absolute relationships like this. One reason is that we need to reject absolute causal relationships if we find any exceptions to it. For example, suppose that we observe 1 million people who play with fire and burn their hand. But we also observe one person who plays with fire but does not burn her hand. Our absolute causal relationship would not be true because of that one exception. This is an unrealistic standard because many of our causal relationships that we're interested in do not exhibit perfect relationships. Also, man-made measurements are not perfect. As a result, scientific causal models are usually probabilistic in nature. Let's see what this means in our example. Our model might say that the chances of burn hand being yes will be higher when play with fire is yes than when play with fire is no. For the purposes of this presentation, what's important to remember is this. Scientific causal models are not typically specified in absolute terms. They are specified, even if only implicitly, in probabilistic terms. Causal models, or theories in science, aren't static. Rather, scientific theories are almost always evolving. As we gain deeper understanding of a phenomenon, we refine our causal models to reflect that deeper understanding. Let's illustrate this idea of refining scientific models with our example. You might gain a new insight that the real cause of burning hand is not playing with fire per se, but how close you are to the fire when you're playing. That is, if you play far away from the fire, you rarely, if ever, get burned. But if you play near the fire, even if you're not playing with the fire itself, you tend to get burned. So you decide to refine your causal model by replacing the independent variable play with fire. You replace it with a variable called distance to fire. While play with fire was a categorical variable whose value was either yes or no, distance to fire is a numerical variable. The variable provides a more refined model of how people burn their hands when playing. As the distance to fire decreases, the chances of burning one's hand increases. Redefining the independent and dependent variables is one way that scientists improve their theories. We conclude this section on modeling causality with a final point on notation. In this presentation, we explicitly display the if and the then in our illustrations. In the research literature, causal relationships are depicted more simply. Causal relationships are typically illustrated with a simple arrow. The reader is presumed to understand that the tail of the arrow starts from the cause, or the independent variable, and the head of the arrow points to the effect, or the dependent variable. That concludes the second part of the presentation. Let's quickly review what we discussed in this presentation. We began with the question of how causality is conceptualized in scientific research. It is viewed as if-then rules that link cause and effect. Next, we discussed how causal relationships must be modeled for scientific experiments to test them. The concept of cause and effect must be operationalized as independent and dependent variables that can be measured. This concludes this introduction on causal relationships in scientific research.